My name is Smart White Kid, so today we're going to talk about the question 1. So as you can see that we'll calculate the mean first, and let's look at the data first. We have 7 expenditure cards, and each with a midpoint and a frequency represent their number and all the number of students in each range. So in order to find it, we will multiply each uh, midpoint by frequency and then sum those products and then divide it by the total number of students. And here is our calculations. And the total number of students is 114, and this is our sum of what I've just mentioned. And the total amount is $7,116. And then we're going to calculate the mode. And then in the most, we're going to find the highest frequency class. And so it's around 5,000 to 8,000. And apply this formula in here, as you can see that. And so we can use the lower class boundary and the class rims and the frequency of the most class and its neighbors. And the calculations give us the most is that's $6,874 Hong Kong dollars around. And then about the standard deviations. For the standard deviations, which measure how spent out the expenditure are. So we'll multiply each frequency by the square of its midterm of its midpoint, and then sum those values and then divide that by the total number of students. And then we will minus the square of the mean and then take the square root in here, as you can see that. And this gives us a standard deviations about $3,755. And then we're going to calculate the skewness, and the skewness is that the Pearson's divided by the standard deviations, and our result is 0.07 around. So it indicates slightly right skews in the data. And then in the question C1C is that let's estimate how many students spent between $8,600 and $12,500. So we're going to calculate the proportions of students in reference class that fall within this range. And in 8,000 and 10,000 class, about 70% of students are included, and in the 10,000 to 50,000 class, around 50% of students are included. So add this up, we estimate around 55 students fall within this expenditure range, as you can see, and all those calculation methods is included. So thank you for listening, and this is the end of my presentation.
Hello, my name is Li Qingyun, whose student ID is 240991444D. I will be presenting question 2. Let's begin with part A. We define 2 events. Let H be the event that a participant has a healthy diet, and let E be the event that a participant exercises regularly. From the problem, probability of H is 0.60, probability of E is 0.45, and the probability of E given H is 0.50. The first question is to find the probability of neither H nor E. First, we find the probability of H and E. This equals probability of E given H times probability of H, which equals to 0.30. Next, probability of H or E equals probability of H plus probability of E minus probability of H and E, which equals to 0.75. Therefore, probability of neither is 0.25, so the answer for Part A question 1 is 0.25. The second question is to find probability of H given not E. The probability of H and not E equals probability of H minus probability of H and E, which equals to 0.30. Probability of not E equals Y minus probability of E, which equals to 0.555. Now, probability of H given not E equals probability of H and not E divided by probability of not E, which equals to 0.5455. So the answer for part A question 2 is approximately 0.5455. Now, part B, we will use Bayes' theorem. We define PQR be the events that the batch is from vendor PQR. Probability of PQR is 0.40, 0.35, 0.25 respectively, and failure rate is 0.03, 0.05, and 0.07 respectively. We let F be the event that we find exactly one faulty component in a sample of 15. First, calculate the likelihoods using the binomial formula. For P, probability of F given P equals 15 choose 1 times 0.03 to the power 1 times 0.97 to the power 14. This is approximately 0.2938. Similarly, for Q, approximately 0.3658. For R, approximately 0.3801. Now, apply Bayes' theorem. Numerator for vendor P is 0.2938 times 0.40, which equals to 0.11752. The denominator is the sum for all vendors. For P, 0.11752 plus for Q, 0.12803 plus for R, 0.095025. Adding them up gives 0.340575. Then the probability the batch is from vendor P is about 0.3451. That concludes my presentation. Thank you.
Hello everyone, I'm Li Chengyang, whose student ID is 241033855D. I'm going to present the question 3. Firstly, for part A, the first question asks what's the probability that a randomly chosen package is underweight. So we are looking for the probability that the weight is less than 300 grams. So the corresponding z-score should be 300 minus 310 divided by 8. So the z-score is minus 1.25. From the standard normal table, the answer should be 0.1056. The second part asks find the weight which only 5% of packages are lower than. So we know that for standard normal distribution, the z-value for the first percentile is about minus 1.645. So we convert back to the original scale, mean plus z times standard deviation. So the answer is 296.84 grams. For the third question, now we take a random sample of 20 packages. What's the probability that the sample mean weight is between 308 and 314 grams? The sample mean also follows a normal distribution with the mean equals to 310 and the standard deviation equals to 8 divided by the square root of 20. Then we convert the initial boundaries to corresponding z-scores. According to statistical table, the final answer should be 0.856. Now let's go to the second problem. Firstly, we find the probability that a single day has at most one complaint. According to the formula of Poisson distribution probability, the satisfying condition probability is 0.406. Now let variable y be the number of such days, which follows a binomial distribution with n equals to 31 and p equals to 0.406. Here we can have two solutions. The first one directly calculates the answer by binomial distribution. So the answer is 0.1435. For the second solution, since n is equal to 31, which is larger than 30, so by central limit theorem, we can use the normal approximation. with the mean equals to n times p and a variance equals to n times c times 1 minus p. After applying continuity correction, we now need to find the probability of y is larger than 15.5. So with the approximation from the statistical table, the final answer is 0.1423, which is close to our previous solution result. So that's all for this question 3.
Hi, my name is Huang Junhao, and my student ID is 24109866D, and I will be presenting question 4. So for part A, we are calculating 99% confidence interval for difference in proportions. So step 1 will be calculate the sample proportions, p hat. So for sample 1, n1 equals to 400, x1 equals to 220, and the proportion will be 220 over 400, which equals to 0.55. For sample 2, we have n2 equals to 400, x2 equals 330, so the proportion will be 330 over 400, which is 0.825. Next, we need to find the difference. So 0.825 minus 0.55, which equals to 0.275. This is the point estimate. Next, we need to find the critical value and standard error. Since we need a 99% confidence interval, we look at the table and the critical value is 2.576. Now, for the standard error, we just use the formula. After plug the numbers in, we got the answer 0.0313, and we have the everything to build the interval. So 0.275 plus minus 2.576 times 0.0313, which gives us a lower bound of 0.1944 and upper bound of 0.3556. Moving to part B, we are calculating the probability of differences in sales. So we are comparing two salespersons. We know that their daily sales are normally distributed with the same sample mean. Because they have the same sample mean, the expected difference between them is 0, but the standard deviation are different. So standard deviation for salesperson 1 will be 200. Standard deviation for salesperson 2 will be 250. The sample size for both of them are 10. The second step, we need to find the standard deviation for this difference between their sample means. We just use the formula and plug the numbers in. This gives us a standard error of approximately 101.2423. Step 3 will be calculating the z-score. We also use the formula, so 150 over 101.2423, which gives us a z-score of 1.48. Then if we use the statistical table, the answer would be 0.0694. But since the question asks for a difference of at least 150, this could be person A sells 150 more than person B, or person B sells 150 more than person A. This is two-tailed situation. So we need to times the probability by 2. The final answer will be 2 times 0.0694, which equals to 0.1388.
My name is Waijilo. I'm going to explain the question 6 of set A. In this question, we are looking at whether the number of defective bolts in each box of 5 following a binomial distribution. First, the binomial distribution has parameter n and p. But we are not given p, so we need to emit it from the sample. We can use sum of 5 times Fi to expect the number of bolts because each ball has 5 bolts. Also, we can find the number of defectives both by sum of Fi's times Si. So we can calculate the probability of defective balls now by number of defectives divided by total number of balls and find Q by Q equal to 1 minus P. Next, using this P equal to 0.061, Q equal to 0.939, and N equal to 5, we can compute the binomial probabilities for the numbers of defectives in a box, and then time 400 to get the expected frequency. Don't expect the frequency work out directly as the bottom left, so that we need to combine 2, 3, 4, and 5 into a single class called 2 or more. Because the express cost of 3 to 5 are too small for the chi-square test, which are both smaller than 5. Therefore, we can get the new list on the right side. Then we can use this formula to find the chi-square statistic, which is about 45.5. After that, we need to find the degrees of freedom. We now have 3 cells and 1 emitted per meter P. According to the degrees of freedom equal to number of cells after combustion minus 1 minus number of per meter emitted. The degree of freedom should be equal to 3 minus 1 minus 1, which is equal to 1. And at the 5% level, the critical square value of 1 degrees of freedom is about 3.84. Our test statistic 45.5 is much far larger than 3.84, so we can reject the hypothesis. And the conclusion is that at the 5 significance level, the observed distribution of defective per box is significantly different from a binomial distribution. This suggests that the assumption of concept is independent defect probability per box do not hold for this process.